What's up? Welcome to another Stack Lessons session. 20 questions ahead on AI Gateway Guardrails, Inference Table Behavior, and RAG Retrieval Patterns. Read each one. Use the 10-second timer, then check your answer against the reveal and the explanation. Take notes if it helps. Okay, question 1. Do not stop at the first match. A generative AI engineer at Summit Lending is building a real-time loan recommendation assistant using feature serving. The application must retrieve each borrower's pre-materialized credit tier from an online feature store, and then compute a derived risk score by applying a transformation to that credit tier at inference time. Which two feature spec components should the engineer combine to implement this design? Select 2. Review the answer choices on screen. The correct answers are option A and option C. Feature spec needs two components working in tandem. Feature spec is the configuration object for a feature-serving endpoint, and is composed of two complementary component types. Feature lookup retrieves pre-materialized feature columns from an online feature store using a primary key, covering the credit tier already computed and stored upstream. Feature function applies a user-defined transformation at inference time, computing derived values such as the risk score on the fly from the retrieved features. Together they handle both the pre-materialized and on-demand feature patterns within a single endpoint call. Inference table is a separate model serving capability for logging endpoint traffic and is not a feature spec component. Databricks embeddings is a LangChain integration for generating text vector representations and plays no role in structured feature retrieval or transformation. Vector Search Retriever performs semantic similarity search over an embedded corpus and is not part of the feature-serving feature spec design. Let's slow down on this one. Knowing which two feature spec pieces to combine is worth understanding properly. Imagine a loan app where borrower credit tiers are computed in a nightly batch job and saved to a database. At request time, you just need to pull the right row. That's feature lookup. It does a key value fetch from the online store. Give me credit _ tier for borrower 42. But the risk score can't be pre-computed. It's a formula you apply right now, on each request. That's feature function. It runs your transformation live, on the spot. The inference logger, text embedder, and vector searcher, all real Databricks tools, just not feature spec components. The question rewards knowing you need one to fetch and one to compute. Here we go. Question 2. Reason from the scenario. A knowledge management startup is building a document retrieval system where users search using a mixture of exact product codes, like SKU-AB 1234, and semantic descriptions like noise-canceling wireless headphones. Pure dense vector search misses exact SKU matches. Which AI search feature should the engineer enable to handle both query types in a single retrieval call? Select 1. Review the answer choices on screen. The correct answer is option B. Exact codes and semantic queries need different matching engines. Hybrid search in Databricks AI Search combines BM25 keyword scoring, which excels at exact token matches like product codes, with dense vector similarity, which captures semantic meaning and merges the two ranked lists using reciprocal rank fusion into a single response. This single call handles both query types without maintaining separate systems. Storage-optimized endpoints improve throughput and indexing speed for very large corpora, but do not address the dual query type retrieval problem. A separate full-text index would require manual result merging and additional infrastructure. Parent-child retrieval improves context delivery after a document is retrieved, but does not solve the problem of matching exact codes in the initial search phase. Here we go. Let's work question 3. A generative AI engineer at Harbor Analytics has deployed a customer service LLM through AI Gateway. The company's compliance team requires that customer personally identifiable information, including email addresses, social security numbers, and phone numbers, must never reach the underlying model. Which AI gateway feature should the engineer configure to meet this requirement? Select one. Review the answer choices on screen. The correct answer is option D. Compliance means PII never reaches the underlying model. AI Gateway's PII detection and redaction feature identifies sensitive personal identifiers, such as email addresses, SSNs, and phone numbers in incoming requests and replaces them with generic placeholders before the request is forwarded to the underlying model. This satisfies the compliance requirement that PII never reaches the model while still allowing the request to be processed and answered. Rate limiting controls the volume of requests from individual users or groups within a specified time window, and does nothing to prevent PII from passing through to the model. Safety filters are designed to block categories of harmful content such as hate speech and violent language, not to detect or redact personal identifiers. Traffic splitting routes a fraction of requests to alternative endpoints for experimentation or canary deployments, and does not provide any mechanism for inspecting or sanitizing request content. Next up, question 4. Separate context from noise. A generative AI engineer at a financial services firm is building a RAG application that must answer questions using both annual reports stored as PDFs and live portfolio holdings stored in a relational database. Which architecture correctly handles both data sources in the RAG pipeline? Select one. Review the answer choices on screen. The correct answer is option B. Each data type earns its own retrieval method. Unstructured documents such as PDFs are best served by embedding-based vector retrieval because meaning is distributed across free-form text. Structured relational data is best accessed through SQL, which can apply precise filtering, aggregation, and joins that embeddings cannot replicate faithfully. Combining both in the augmentation step grounds the prompt in a semantically relevant document passage alongside an accurate, current data value. Converting relational tables to PDFs adds unnecessary conversion overhead while destroying the structural relationships that make SQL powerful. Serializing rows as JSON for embedding degrades retrieval precision because embeddings over structured key value text are far less reliable than SQL for exact lookups and aggregations. Appending all relational data statically to every prompt bloats token usage proportionally with database size and injects irrelevant portfolio data into every single request regardless of the query. Next up, question 5. Do the logic before the recall. A generative AI engineer at a telecommunications company is preparing to launch a customer support chatbot that completed successful beta testing. The chatbot is expected to handle a minimum of 15,000 queries per hour during business hours, with occasional traffic spikes. The engineering lead wants to ensure consistent latency and predictable capacity for this production rollout. Which serving configuration should the engineer implement for the foundation model endpoint? Select one. Review the answer choices on screen. The correct answer is option D. Production traffic demands a guaranteed capacity floor. Provisioned throughput is the recommended configuration for all production workloads because it allocates dedicated model capacity, guaranteeing consistent throughput and predictable latency. Specifying both min_provisioned_ throughput and max_provisioned_ throughput lets the endpoint scale between defined bounds while ensuring the minimum token per second floor is always available. Pay-per-token endpoints are designed for early development and experimentation, not high-volume production deployments, and they do not provide the latency consistency required once traffic is substantial. A pay-per-token endpoint with a rate limit throttles requests rather than guaranteeing a minimum service level, which would hurt the user experience under load. Omitting the minimum throughput parameter on a provisioned endpoint does not establish the capacity floor needed to protect against degradation at the stated traffic volume. Opening 5 lock in 2 patterns. PII redaction is a distinct guardrail from safety filtering, and provisioned throughput with min and max bounds signals every production workload question. Next up, let's handle question 6. A generative AI engineer at Brixton Analytics has built a legal document summarization service on Databricks that processes approximately 5,000 requests per hour consistently throughout business hours. During development, the team used pay-per-token pricing. The service is now ready for production. Which serving pricing model should the engineer migrate to? Select one. Review the answer choices on screen. The correct answer is option B. Pay per token is dev. Provisioned throughput is production. Provisioned throughput is the Databricks recommended serving model for all production workloads. It provides consistent latency, predictable performance, and is configured by specifying minimum and maximum tokens per second thresholds that guarantee capacity regardless of traffic bursts. Pay per token pricing is appropriate for development and exploratory phases, but is not recommended for high-throughput production use, where sustained, predictable load makes provisioned capacity more cost-effective and reliable. Routing through an external model via AI Gateway introduces a third-party dependency and does not address the serving tier decision for the internal service. Storage-optimized endpoints are an AI search configuration for indexing large vector corpora and have no bearing on model serving pricing. Let us keep moving. For question 7, the qualifier matters. A machine learning team at a logistics company uses feature serving to expose delivery route features to a production model endpoint. A data governance audit requires them to demonstrate which upstream data sources and transformations contribute to each feature served in production. Which Databricks capability addresses this requirement? Select one. Review the answer choices on screen. The correct answer is option C. Lineage and logging sound alike but solve different problems. Unity Catalog feature lineage automatically captures the provenance chain from upstream source tables through feature definitions and transformations to the serving endpoint. This gives governance and audit teams a queryable record of exactly which data assets underlie each feature exposed in production, satisfying data lineage audit requirements without additional instrumentation. MLflow experiment runs record training time artifacts, such as hyperparameters and evaluation metrics, but do not trace the runtime data lineage of production features. Inference tables capture the request and response payloads at the serving endpoint, which is useful for monitoring model behavior but provides no information about upstream data sources. AI Gateway traffic tracking logs usage volume and cost attribution for billing governance, not the data transformation lineage that a data governance audit requires. Let us keep moving. Question 8. Check whether it asks what or why. A generative AI engineer at Montrose Media is building a product catalog enrichment service. Each product listing contains a written description and a product image. The service must analyze both the text and the image in a single model call to generate an enhanced product description. Which foundation model API model should the engineer use? Select one. Review the answer choices on screen. The correct answer is option D. Text plus image in one call means true multimodal only. Gemini 2.5 Flash is a multimodal model available through the Databricks Foundation Model API that natively accepts text and image inputs together in a single inference call, making it the correct choice for enriching product listings that combine written descriptions with product images. BGE Large is an embedding model that converts text into fixed dimensional vectors for retrieval and similarity search, It produces no generated text output and cannot interpret image content for description generation. Code Llama 34B is purpose-built for generating and analyzing programming code across multiple languages and has no training specialization for image understanding or catalog description generation. Llama 3.370B Instruct offers a 128K token context window and strong language generation capabilities, but supports text inputs only within the Foundation Model API and cannot natively ingest images for multimodal inference. Time for another one. Question 9. Do not skim the condition. A generative AI engineer at Tailspin Media is building a content cataloging system that must process both still images such as album artwork and thumbnails, and short video clips such as trailers and previews. The system uses a single Foundation Model API endpoint to generate textual descriptions of visual content for search indexing. Video processing is a hard requirement and cannot be delegated to a separate pre-processing step. Which model should the engineer select? Select 1. Review the answer choices on screen. The correct answer is option C. Video is the decisive word hiding in the requirements. Gemini 2.5 Flash is the correct choice because Gemini family models available through the Foundation Model API natively support all 4 input modalities: text, image, video, and audio. This native video support is the decisive differentiator that allows a single model call to process both thumbnail images and video clips without any additional pre-processing pipeline. Claude Sonnet 4.6 supports text and image inputs within the Foundation Model API, but does not support video as an input modality, making it incapable of natively ingesting video clips for content description. Llama 4 Maverick similarly supports text and image inputs only, and cannot process video content without a separate frame extraction step that routes the workload outside the model's native capabilities. BGE Large is an embedding model that produces vector representations for retrieval and similarity search. It cannot interpret visual or video content, cannot generate descriptive text output of any kind, and has no generative capability. Let's slow down on this one. Video support is the trap, and it changes everything. Imagine you're building a catalog for Tailspin Media. You have 10,000 assets, thumbnail JPGs and 30-second trailer clips. You need one model call to handle both. Most models in Databricks handle text and images just fine, but video? Only the Gemini family goes all the way. Gemini 2.5 Flash takes all 4, text, image, video, and audio, natively in a single call. No pre-processing needed. Claude Sonnet 4.6 stops at images. Llama 4 Maverick stops at images too. On Databricks, BGE Large is a pure embedding model. It produces vectors, not descriptions. That's the trap. Only one option clears the video hurdle. Let us keep moving. Let's work question 10. Quick check. A generative AI engineer at Alpine Analytics is logging a large model checkpoint file to MLflow as an artifact. The checkpoint is 8 GB. The upload fails with an error. What is the most likely reason? Select 1. Review the answer choices on screen. The correct answer is option A. MLflow caps every single artifact at 5 GB. MLflow enforces a maximum file upload and download size of 5 GB per artifact. An 8 GB checkpoint file exceeds this limit and will cause the upload to fail regardless of which artifact backend is configured. The 5 GB limit applies uniformly across DBFS, Unity Catalog volumes, and Amazon S3 storage backends. There is no format restriction on artifact logging. Arbitrary files including raw model checkpoints are fully supported. No compression requirement exists for large artifacts in MLflow. 6 through 10 add 2 anchors. MLflow's 5 GB artifact ceiling and Gemini 2.5 Flash's native video support. which neither Llama 4 nor Claude can match through the Foundation Model API. Ready. Question 11. Match the answer to the situation. A generative AI engineer at Barfield Systems has enabled an inference table on a model serving endpoint that processes legal briefs submitted as raw text. During a compliance audit, the team discovers that certain requests are entirely absent from the inference table log. Investigation reveals that the missing requests all involve full legal briefs averaging 12 megabytes per payload. What is causing the missing log entries? Select 1. Review the answer choices on screen. The correct answer is option A. 10 megabyte is the per payload ceiling, not 5 gigabytes. Inference tables have a maximum payload size of 10 megabytes per request-response pair. Any request whose payload exceeds this threshold is silently omitted from the table, which directly explains why 12 megabytes legal brief submissions are not appearing in the compliance audit log. The 5 gigabytes limit applies to MLflow artifact file uploads and has no bearing on inference table logging behavior. Inference tables capture successful requests by default. It is error responses with status codes such as 401, 403, 429, and 500 that may not be logged, not the successful 200 status responses. The 128 concurrent request limit governs the number of simultaneously active connections to the endpoint. Once those requests complete, they are eligible for logging and are not permanently excluded from the inference table on account of having been queued. Let's pause here. This one trips people up because the answer hides in a size limit. Picture a compliance auditor noticing that some legal briefs are missing from the inference table log. Why? Databricks inference tables silently skip any request bigger than 10 megabytes. Barfield's briefs average 12 megabytes. That's roughly 11.4 megabytes over the limit. No error, no warning, just gone. Now, Distracted D mentions a 5 gigabytes limit. That's for MLflow artifact uploads, a completely different system, and inference tables DO log successful 200 responses. It's error codes like 401 and 429 that can be skipped. The punchline: size alone triggers silent drops, and the exam tests whether you know that 10 megabyte ceiling. Ready. Question 12. Watch the almost right choices. A generative AI engineer at a retail analytics company has configured an inference table on a production-serving endpoint to capture all requests and responses for a product recommendation model. A database administrator renames the underlying Unity catalog table from prod_catalog.serving.rec_model_logs to prod_catalog.serving.rec_model_logs_v2 to match a new naming convention. What is the immediate consequence for the inference table? Select 1. Review the answer choices on screen. The correct answer is option A. Rename outside the endpoint config severs the logging link. Inference table logging stops whenever the underlying table name is changed, the table schema is altered, or the table is deleted. The serving endpoint retains a reference to the original table name as set at configuration time, and does not follow renames made outside of the endpoint configuration. Once the referenced path no longer resolves to a table, the endpoint silently stops writing new records. The existing historical data stored in the renamed table is not deleted by the rename itself, only new incoming records stop being captured. Unity Catalog does not provide automatic follow-on rename behavior for inference table references. The pause and resume behavior described does not occur. The stoppage is permanent until the endpoint is explicitly reconfigured to point to the updated table name. Let us switch gears. Question 13. Identify the business need first. A generative AI engineer at a financial services firm has deployed a foundation model API endpoint through AI Gateway for use by internal analysts. During quarterly reporting periods, A small set of power users sends extremely high request volumes, causing timeouts for other analysts. The engineer needs to enforce equitable access without modifying the model, the serving infrastructure, or the client applications. What should the engineer configure? Select 1. Review the answer choices on screen. The correct answer is option B. User-level rate limits are the native equitable access fix. AI Gateway natively supports rate limiting that can be enforced at the endpoint level, the individual user level, or the group level. Configuring per user rate limits caps how many queries any single analyst can submit per minute, ensuring equitable access across the team without any infrastructure changes or client modifications. A second endpoint with DNS round-robin doubles cost, but does not prevent individual power users from monopolizing whichever endpoint they reach. Increasing provisioned throughput accommodates higher total capacity, but leaves power users free to consume the expanded headroom, recreating the same fairness problem. A custom queuing microservice introduces significant development and operational overhead for a problem that AI Gateway rate limiting resolves natively. Let us switch gears. Question 14. Ignore details that do not change the decision. A generative AI engineer at Summerfield Labs is launching a new internal knowledge assistant that will be piloted with 20 employees for 6 weeks before any broader rollout. During the pilot, daily usage is expected to be light and highly unpredictable. If the pilot succeeds, the tool will scale to 4,000 employees with consistent daily traffic. Which serving configuration should the engineer use during the pilot phase? Select 1. Review the answer choices on screen. The correct answer is option A. 6 weeks and 20 users. Do not pre-buy capacity. Pay-per-token foundation model API endpoints are the recommended starting point for exploratory, low-volume workloads, where usage is uncertain and a fixed capacity commitment cannot be justified. During a 20-person pilot with variable daily demand, costs align directly with actual consumption and no upfront capacity planning is required. Provisioned throughput endpoints are the appropriate choice for production workloads that require guaranteed latency under sustained load, but committing to dedicated model units for a small pilot is economically wasteful and premature. Storage-optimized AI search endpoints are designed for high-scale vector retrieval and play no role in serving LLM completions. A custom model endpoint scaled to 0 introduces cold start latency whenever usage resumes after an idle period, degrading the pilot experience without meaningful cost savings relative to the pay-per-token option. Keep your focus here. We're on question 15. A generative AI engineer at Radcliffe Insurance is deploying an LLM-powered claims assistant that processes customer support messages. Compliance requirements prohibit social security numbers and email addresses from being transmitted to the underlying model. Which AI gateway feature should they configure to enforce this requirement automatically? Select 1. Review the answer choices on screen. The correct answer is option C. PII redaction replaces sensitive data automatically before the model. PII detection and redaction is the AI gateway feature designed specifically for preventing structured sensitive data from reaching the model. It automatically identifies regulated data formats including social security numbers and email addresses within the request payload, and replaces them with anonymous placeholders before forwarding the message to the underlying LLM. This allows conversations to continue without the model ever receiving the regulated data, satisfying compliance requirements without rejecting requests entirely. Safety filtering targets content categories such as hate speech, insults, sexual content, and violence. It does not recognize structured data formats like SSNs or email address patterns. Rate limiting enforces request volume constraints per user, group, or endpoint, and does nothing to inspect or modify the content of individual requests. Traffic tracking records usage for cost attribution and auditing purposes, but does not alter or block any content in transit. The inference table cluster delivers one repeating rule: any external rename or schema change silently kills logging. The serving tier split also solidifies pay per token for pilots, provisioned for production. Alright, question 16. Watch the exact wording. A generative AI engineer at Pemberton Legal is building a discovery assistance tool that retrieves case-relevant documents from a large legal corpus. The attorney's overriding concern is ensuring that no relevant document is overlooked, even if some irrelevant documents also appear in the results. Which retrieval quality metric should the engineer prioritize when evaluating the retrieval component? Select one. Review the answer choices on screen. The correct answer is option C. No relevant document left behind means recall, not precision. Recall at K measures the fraction of all known relevant documents that the retrieval system surfaces in its top K results, making it the correct choice when completeness is the overriding requirement. In a legal discovery context, failing to surface a relevant document can have serious consequences, so maximizing recall is prioritized over avoiding irrelevant results. Precision at K measures the proportion of retrieved documents that are relevant and would penalize a system for returning irrelevant results alongside relevant ones. This is the wrong trade-off when missing relevant documents matters more than filtering noise. NDCG at K evaluates the quality of the result ranking and rewards placing the most relevant documents highest, but it does not specifically capture whether all relevant documents were retrieved in the first place. DCG at 10 captures relevance intensity and ranking position, and is useful as a general-purpose default metric, but it does not specifically optimize for the completeness concern that defines this legal use case. Alright, question 17. Likely distractors ahead. A generative AI engineer at Holloway AI deployed a customer chat assistant with an inference table configured to capture all requests and responses. During a scheduled maintenance window, the operations team renamed the inference table to align with a new naming convention and added 2 audit columns to its schema. After the maintenance window, the endpoint is no longer writing any data to the table. What caused logging to stop? Select one. Review the answer choices on screen. The correct answer is option B. Both rename and schema change are separately documented stoppers. Databricks inference tables are tightly coupled to the exact table name and schema that was specified when the endpoint was configured. Renaming the table or modifying its schema are both documented operations that cause the endpoint to stop logging immediately. Deleting the table has the same effect. The platform does not automatically adapt to table renames or schema evolution, so the engineer must reconfigure the inference table setting on the endpoint, pointing it to a new table with the correct name and schema to restore logging. The sampling fraction is a manually configured setting between 0 and 1 that does not reset automatically during maintenance operations. The 128 concurrent request limit is a throughput constraint on in-flight requests and does not trigger any mechanism that disables logging. Inference tables persist as Unity Catalog Delta tables until explicitly deleted, and have no 30-day automatic rotation or expiry. Okay. Question 18. Several choices sound plausible. A generative AI engineer at Ashbourne Legal is deploying a client-facing chatbot that handles routine legal inquiries. The compliance team requires that social security numbers and email addresses appearing in client messages be replaced with neutral placeholders before reaching the model, and that any model response containing a phone number be suppressed entirely rather than delivered to the client. Which combination of AI gateway guardrails satisfies both requirements? Select 2. Review the answer choices on screen. The correct answers are option A and option C. Request side redacts, response side blocks entirely, two different jobs. PII detection and redaction on the request replaces detected fields such as SSNs and email addresses with generic placeholders before the prompt is forwarded to the model. The message still reaches the model, but with sensitive values removed. PII blocking on the response suppresses any model output that contains detected PII, such as phone numbers, before it reaches the client, fully preventing delivery of that content. Safety filtering is designed to block content involving hate speech, violence, or sexual material, and does not identify or act on personally identifiable information fields. Rate limiting controls the volume of requests through an endpoint, and has no capability to inspect or redact PII content within individual responses. PII redaction on the response would replace phone numbers with placeholders rather than suppressing the entire response, which does not satisfy the requirement to withhold such responses entirely. This one trips people up. Let's map out which guardrail does what and when. Imagine a legal chatbot. A client types their social security number into the chat. You don't want that SSN sitting raw in the model's prompt, so you apply PII redaction on the request. It swaps the SSN and email with placeholders. The model sees clean input. Now flip it. The model's reply includes a phone number. Your compliance team says kill that response entirely. Don't even deliver a cleaned version. That's PII blocking on the response. The whole message is suppressed. The client gets nothing. The trap is option E. PII redaction on the response just swaps the phone number for a placeholder. It doesn't wipe the reply. Suppress versus sanitize. That's the exam's real question. Okay. Question 19. Map the scenario to the capability. A generative AI engineer is building a RAG application over lengthy insurance policy documents. Evaluation shows that retrieval is accurate. The correct policy sections are consistently returned, but the LLM frequently produces incomplete or out-of-context answers because individual retrieved chunks lack the surrounding clauses needed to interpret the matched text. Which chunking strategy directly resolves this mismatch between retrieval precision and generation context quality? Select one. Review the answer choices on screen. The correct answer is option A. Index small for precision, retrieve larger parents for context. Parent-child retrieval resolves the precision-context trade-off by operating at two granularities simultaneously. Small chunks of approximately 512 tokens are indexed in the vector store, ensuring retrieval stays precise and specific policy clauses are consistently matched. When a chunk is retrieved, its larger parent segment of approximately 2048 tokens is passed to the LLM, supplying the broader surrounding context needed for complete and accurate generation. Increasing uniform chunk size to 2048 tokens improves context richness, but reduces retrieval precision because embedding a very large segment dilutes the signal of specific clauses and degrades recall. Semantic chunking produces coherent topic segments, but does not specifically address the gap between retrieval granularity and the context richness the LLM requires. Reducing overlap to zero worsens boundary context loss and provides no benefit to what the LLM receives after retrieval. Let's slow down here. This is exactly the kind of question the exam loves to test. Imagine you have 200 pages of insurance policy text. You search for flood exclusion clause and find the exact sentence, but that sentence says subject to section 4.2. Without section 4.2, the LLM is stuck. That's the gap. Parent-child retrieval fixes it with two layers. You index tiny 512 token chunks for sharp search. Each chunk has a pointer to its larger 2048 token parent block. When search finds a match, you swap in the parent block before the LLM ever sees it. Precise retrieval, rich context, at the same time. The other options force a trade-off. This one doesn't. That's why it's the answer. Here we go. Question 20. Keep the constraints in view. A generative AI engineer at Bridgewater Analytics is designing a RAG application for a financial services firm. The application must answer questions using both unstructured PDF earnings reports stored in a document repository and live structured stock price data from a relational database. How should the engineer architect the retrieval layer to handle both data types correctly? Select one. Review the answer choices on screen. The correct answer is option B. Structured data earns SQL. Unstructured text earns vector search. RAG applications frequently combine unstructured and structured data, and each type is best served by a different retrieval mechanism. PDF earnings reports are well suited to vector search because semantic similarity can identify relevant passages from dense narrative text. Structured stock price data is better queried directly through SQL, which provides exact numerical accuracy, freshness, and the ability to apply filters and aggregations that embedding-based retrieval cannot reliably replicate. Both result sets are then combined with the user query in the augmentation step and passed to the LLM for generation. Converting database rows into PDF summaries loses the precision and freshness of the source data and introduces an unnecessary transformation step. Embedding database rows into a vector index adds approximation error to lookups that have exact keys and should be answered with precise SQL semantics. Routing structured numerical data through vector search risks incorrect retrieval due to the inherent imprecision of nearest neighbor matching for factual and time-sensitive financial figures. 3 takeaways from this session. First, renaming or schema-altering an inference table silently stops all endpoint logging. Reconfigure the endpoint to restore it. Second, only Gemini 2.5 Flash handles text, image, and video natively through the Databricks Foundation Model API. Third, PII redaction removes sensitive identifiers before model access. Safety filtering blocks harmful content, not interchangeable guardrails. AI gateway guardrails that redact rather than block, inference table fragility on any rename, and the vector plus SQL mindset for mixed data. These are live production concerns. Carry that precision forward.